So this time we'll be solving question number 30 from phase 1, book of physics, from the last chapter of it, which is forces and the laws of motion. This is question number 30 from exercise 1 of chapter forces and laws of motion. Let's see the question. According to this question, we have to discuss the apparent weight of a man in lift or elevator actually. So this is about the conceptual apparent weight. Now, when it comes to the apparent weight, what is apparent weight? Okay. As the name suggests, it's the weight which you find it like it's there. Apparent weight. So let's say there is a man standing into this lift, and let's assume the lift is going up with some acceleration. As we know in this chapter, basically, if the lift is going up, then we have two options to look at this man. We can see this man with respect to ground. We can see this man with respect to ground, or we can see this man with respect to the lift. Here, this man is my system. This is the system. Anything which we look at becomes the system. So I'm looking at the system. We are looking at the system. We can look at the system from the ground, or we can look at the system with respect to lift. Now, if I'm looking at the system from the ground, then ground is an inertial thing. And with respect to inertial thing, all laws of motions are valid. So there is no issue in that case. But when I'm looking to the man with respect to the lift, this is my non-inertial frame. And in case of non-inertial frame, laws of motions are not valid. Newton's laws of motions are not valid when we are looking with respect to the non-inertial frame. Now, to make Newton's laws valid in non-inertial frame, we have to introduce a pseudo force. That's what the concept of pseudo force is. So, if I look with respect to this lift, to this man, I need to apply a pseudo force. Once I apply the pseudo force, which is the imaginary force, onto the man, then the laws of motions, Newton's laws of motions are valid there. Meaning we can make the FBD, we can make everything there. So that's one thing. So I'll be looking at this system with respect to the lift, and I need to apply the pseudo force. The second thing is the concept of weight. What's the concept of weight? So please understand, weight does not mean mg. Whenever we talk about the weight, ultimately we'll be measuring the weight with some machine. The weight will be measured with respect to a machine. So you don't know, there is no weight written on your face, basically. You want to calculate the weight, you have to go for the machine. So there are two types of machine generally there are. One is basically where you stand. So if you are standing on the machine, which will be telling your weight, the machine won't be telling your mg, machine will be telling your normal reaction. Or you can hang with some machine. If you're hanging with a machine, like which is having the spring, the machine will be measuring the displacement in the spring, or you can say the value of kx. So let's assume the man is standing on a machine. If the man is standing on a machine, the machine will be measuring the normal reaction, not the weight, first of all. Now, the thing is, normal reaction it will measure. In some cases, the normal reaction will be mg, but in some cases, it won't be mg. That's the difference. When normal reaction is mg, we say it's a weight, and when the normal reaction is not mg, it is changing, we start saying it's apparent. So, when I'm talking about the apparent weight, we are talking about the normal reaction ultimate. So, I'll make the FBD with respect to this man. Okay. FBD means I'm making two coordinate systems. This coordinate system is for the acceleration, and this coordinate system is to show the forces. Let me put the acceleration first. So, I'm looking with respect to the lift, and with respect to the lift, the man is not moving. Acceleration is 0. There is no acceleration. Now I'll see the force is acting onto the man. So mg is acting downward onto the man. That's a gravitational force. Normal reaction is acting upward onto the man. And then comes the pseudo force. So this lift is going up with acceleration A. Since the lift is going up with an acceleration A, the pseudo force will be acting downward, and the magnitude of the pseudo force will be m into A. So mass of the system multiplied with acceleration of the observer. And the acceleration of the observer is same as the lift, so m into A. This is the pseudo force. Now, if this lift starts going downward, then the pseudo force will start acting upward. Rest of the two forces will be same. So in this case, let's balance it. So if I balance in this case, and since there is no acceleration, so I'll say N minus mg minus ma into m into 0, which is this acceleration. And that gives us the normal action is equals to mg plus ma. As you can see, in this case, normal action is more than mg. That's your apparent weight. Now, in the reverse case scenario, if the acceleration will become downward, this ma will be acting upward. And if the ma will be acting upward, this will be positive here. And if this is positive, here it will be negative. So normal action will be mg minus ma. So normal action will be less than mg. So that's what happened. If the acceleration is, normal action will be same as the mg. If there is no acceleration, there can be velocity. If there is no acceleration, our weight is the actual weight. If the acceleration is up, like in this case, our weight increases. We start feeling that increased weight. But it is not the increased weight, it is the increased normal reaction. And when the acceleration is downward, we start feeling weightlessness. Or you can say we start feeling like our weight is reducing. Again, weight is not reducing. The mass is not reducing. It is the normal reaction which is reducing. Okay. So the normal reaction will keep on changing depending upon the lift is going up or down. That's the concept of apparent weight. So apparent weight is nothing but the normal reaction. Okay.